Hi, C++ and object-oriented programming are popular items these days. When you get by the hype and you've learned the mechanics of programming in C++, and you've learned the limitations of a particular compiler and programming environment, you're still left wondering, how do I use the features of this language to get the most benefits in terms of productivity and quality? The answer is not a list of rules, but a collection of techniques based on experience from implementing real programs. I've been using C++ for about 8 years now, and I'm going to share some of the techniques I've learned from working in a small group that has developed several C++ class libraries and applications. I'm going to start by giving some background about the software I've developed in C++ and define a few terms. Then I'll talk about encapsulation, contrasting the encapsulation of a single class with the design of a group of classes, which is sometimes but not always the same as a class library. I'll use the term library or system or application when I really mean just a collection of classes. I'll give some examples showing the effect of thinking about encapsulation on a group of classes as different from a single class. Then I'll switch to talking about inheritance and distinguish the sharing of interfaces from the sharing of implementations. I'll briefly talk about connecting or wiring objects as a situation where inheritance is tempting but not appropriate. And I'll conclude with a summary and a peek into what people are likely to do in this general area in the near future. The problem domain that I've been concentrating on is user interfaces. It's important that I mention a couple of characteristics of user interfaces that may differ from other domains. First, there's never any question that the implementation of a user interface should be object-oriented. Direct manipulation maps naturally onto an object-oriented implementation because common gestures like clicking or dragging may be implemented differently by different kinds of objects. So I haven't had to justify why am I using an object-oriented language in my work. The second characteristic of user interfaces is that the performance trade-offs are pretty well understood. The time to draw graphics often dominates the time to traverse a set of objects representing those graphics. And user events come relatively infrequently compared to the speed of CPUs. That's really nice. Users are generating interrupts at about the same rate now as we were several years ago, but CPUs keep getting faster and faster. Now, in contrast, if I were implementing something like a linear algebra system, I might run into a different set of problems. In particular, I might want the representations of things like matrices to be abstract, and I'd want algorithms that, like matrix multiply, to use the abstract representations. But I might not be able to afford to do a virtual function call in the inner loop of something like a matrix multiply. So the bottom line is that in user interfaces, we can isolate time-critical areas and avoid inherently expensive interaction between applications and libraries. I think a lot of domains are similar because the abstractions are high enough level and that allows the performance hotspots to be localized. But not all domains are the same. The system that most of my experience is based on is called interviews, which stands for interactive views. I'm currently working on a follow-on system called Fresco that uses many of the ideas from interviews and the techniques that we learned from things we did right and things we did wrong in building interviews. Interviews is a modest-sized system. It's about 100,000 lines of C++ code and was developed by a team of 3 or 4 people. It's in use in a variety of research and product efforts throughout the world. The easiest way to see some of the features of interviews is for me to do a brief demo of Doc, a simple document editor. In Doc, everything is a C++ object, from the simple things like the menus to the text, the figures, the columns, the lines, and yes, even the characters. The base class for these objects is called glyph and provides a uniform model ranging all the way from simple graphical objects like circles or rectangles to traditional UI widgets like buttons and scroll bars, all the way up to full-scale embedded applications. Interviews also includes Unidraw, which is essentially the functionality of a drawing editor like MacDraw, defined in terms of a reusable class library. Now, before going further, I should define a few terms. When I say encapsulation, I mean the separation of interface and implementation. Software, I find, is all about change. We want to separate out the interface so that we can minimize the effects of changing the implementation. If some other code only uses the interface, then it doesn't need to be modified when the implementation is changed. Hopefully, this means lower costs for evolving and maintaining the software. After all, that's the whole idea of this stuff, is that we should make it cheaper to build and maintain our software. Now, inheritance is deriving new interfaces and implementations that share or inherit portions from other classes. Delegation is similar to inheritance, but often you use a forwarding mechanism to a member variable instead of sharing member functions directly. I'm not going to talk about parameterized types, which you use templates for in C++. There isn't time to talk about everything in the language, and the truth is I don't have much personal experience using templates either. The main idea I want to get across about encapsulation is that encapsulating a single abstraction in a C++ class is quite different from encapsulating a group of abstractions in a library or a system. Defining an abstract interface as a single class in C++ usually means three things. First, all member functions are virtual. Second, typically you have no data members. And third, usually you have no protected members. Now, we certainly made the mistake of not following these conventions occasionally in interviews, and we paid the price. When you evolve or port software, you usually make changes that you didn't expect to make. And using virtual functions and no data members in the base classes forces you to keep the implementation flexible enough to handle unexpected changes. One example is the way that we implemented display access in interviews. It made it very difficult to mix interviews and XT widgets in a single application window. Now, this is something we never anticipated doing, but later we saw, wow, that would be a useful thing to have. So we didn't use virtual functions, and as a consequence, it was hard to do. Now, in Fresco, we've of course fixed this. Fresco uses all abstract base classes, and integration with XT has been much easier to implement than it was in interviews. The other thing I mentioned was protected members, and protected members have two problems. First, from a maintenance perspective, protected is really the same as public. If you think about it, either way, one of your customers, somebody who's using your code, will write code that accesses that protected member, or that member. If the member is protected, then it's somebody who writes a subclass. If the member is public, then it's somebody who just uses your class. And either way, they'll be unhappy if you make a change in the future that breaks their code. So from the perspective of somebody maintaining code, protected and public are the same. The second problem with protected is that it really introduces a bias in favor of subclassing over composition. That is, what you're doing is you're telling someone, if you want to access this, write a subclass. But someone who writes a class that simply contains an instance of your class, they can't access it. So you've introduced this bias towards subclassing. And that's really a burden on the person trying to use your class, because you've told them, well, you should do it this way and not the other way. So what we found is that we want more flexibility. We want to let people use it either way. So protected doesn't really help. Now, keep in mind that I'm talking here about abstract classes that define an external interface. I'm not saying that all classes should have all virtual functions, or all classes should have not have member data. That would be a pretty silly statement. The data's got to be somewhere. What I'm saying is that if you're defining an external interface, you want to be careful about what you expose. Now, when you start building larger C++ systems or class libraries or applications that have well-defined pieces, you find that you're not just collecting up a group of abstract classes. The interfaces are really pieces in a puzzle that must fit well together overall to form an interface whose whole is really more than the sum of its parts. And the thing that we learned is that the interface to the whole may actually hide entire classes that exist solely for the implementation. The key to this hiding of the existence of implementation classes is to create objects indirectly, using an object to create another object. Once you make this division, then the implementation classes are by definition not abstract, because they're hidden, and they can certainly have protected members, non-virtual members, and obviously they have data members. I call an object that one uses to create other objects a kit. Now, many people use the term factory to refer to such an object, but having grown up on the East Coast, I think of a factory as something with smoke coming out of it. So to me, the term kit has a more positive connotation. In interviews, we realized we needed kits when we introduced these very cheap objects called glyphs. Originally, like most other toolkits, we had one object for each button, menu item, or scroll bar on the screen. And our objects, like most other toolkits, were pretty expensive. And they were expensive enough that we couldn't afford to create several objects for, say, a single button. Then we started using glyphs, and we said, aha, we can use a bunch of objects to represent a button. And we said, we can split the input behavior and the output appearance into separate objects. This is particularly appealing because we didn't need to define a new button subclass for every different kind of appearance. This is a big problem with a lot of toolkits. If you want to create a button that contains, say, a raster image, you might have to define a new subclass, even if there's already a class that understands button input, and there's already a class that understands how to draw a raster image. With glyphs, we saw we could use composition to create objects more easily. We could also see that exactly how much subclassing was used and how much composition was used really depended on the implementation, not the interface. You know, the programmer doesn't care how the button is created. They just want a button. They want a push button, or they want a checkbox. They want some kind of button. So what we did is we defined a widget kit, an object that creates common widgets like buttons, menus, and scroll bars. So you might have code like b equals widget arrow push button of some parameter list, and this calls the push button function on the widget kit object and gets back a newly created button. So you see the library interface has now hidden the decision of whether to use subclassing or composition. So that button could be implemented by a subclass, or that button could be implemented by composing several other objects. Now, we ran into a more striking effect when we used this approach on layout objects. Now, layout in interviews is modeled after the TEC document formatting system developed by Don Knuth. It's a very rich model for document formatting, and we extended the model, which includes this notion of stretchability and shrinkability, to all objects. In TEC, only white space can be stretched or shrunk. But in interviews, we made every glyph have some geometry that could be flexible. So we could have an image, or a character, or the spacing between characters, or a box containing other glyphs. These were all glyphs, and they were all stretchable or shrinkable. Now, we also refer in TEC speak to the spacing between objects as glue. This is the stuff that's stretchable or shrinkable in TEC terminology, and it's typically oriented horizontally or vertically. Looking at the various classes we had for layout, we didn't see the same sort of subclassing composition trade-offs as for widgets, but we did notice that many classes only defined a constructor and basically just existed for creating instances. Introducing a layout kit, we simply changed code from something like new vglue of 10, which involved a vglue class and various constructors on it. We changed that to calling a member function on the layout kit vglue. So you do something like layouts arrow vglue of 10. Since the vglue class only defined a constructor, we were able to eliminate the vglue class completely. And we did that by making the vglue member function actually create a base class glue object. So now it turns out the glue class doesn't really define any new member functions. So we're also able to remove the glue class from the public interface to the library. The glue class still exists, but people using the library can't see it anymore. And that's because they don't really need to see it, because the only reason it needed to be there was for creating objects. We've now abstracted that by putting in this layout kit. And that means that glue doesn't appear anywhere in any of the interviews include files. Here's a picture of the class library for the classes we originally had for layout. You can see there are lots of classes here. They do lots of things. After switching to using a layout kit interface, we'll see that only a few classes remain visible. Now, some of the classes that got removed, like glue, became hidden. That is, they're still there, you can't see them anymore. Others, like vglue, were actually eliminated completely. And you can see that a fair number of classes went away. All the classes removed from the interface had one thing in common. They didn't add any new operations other than constructors, at least not any operations that we wanted to be visible outside the library. So that's really important. A class that simply re-implements one or more member functions from base classes is really an implementation class. And even the existence of these implementation classes should be hidden. Now, despite my earlier comments about performance and saying we understood all the performance issues in user interfaces, I always worry about adding unnecessary overhead, particularly if I'm just sort of building it into the library and it's not obvious what it's adding. So I was concerned about the cost of adding this level of indirection with kits. But looking closer, you can see that using kits is at least as good and maybe even better than calling constructors directly. Eliminating classes like vglue reduces the number of virtual function tables, which reduces the memory size of your library or your application. Now, memory size is the critical resource these days because CPUs keep getting faster and faster, but the market doesn't seem to be willing to increase base memory configurations, at least not at the same pace. And the other thing that's happening is that users will put lots of icons and windows and all sorts of stuff on their screen, but typically they aren't running more applications concurrently. So you're putting more stuff on the screen, you're adding more CPU power, you're not really running more things in parallel. You may be running lots of different things, and you're not adding to the base configuration of the memory in your system. So that says memory is very important. So it's good that we can save memory. Kits have a couple of extra benefits. One is that you avoid the surprises associated with implicit conversion that C++ performs with constructors. Implicit conversion is one of my favorite features because it can really catch you when you're not expecting it. My favorite example of this comes from teaching concurrent programming, where I really enjoyed giving students an abstract definition of a semaphore. So here's the public part of the C++ class declaration. And you can see that it's really nice, particularly as a teaching aid, because the only operations you can do on it are to create a semaphore with some initial count, and then all you can do to it is you can do a wait or a signal, and wait waits until the count is positive and then decrements the count, and signal increments the count. These are the usual semaphore operations. And I must say it's great to be able to give this to people and say, don't worry how it's implemented, just use it. So a student came up and said, I'm trying to use this semaphore class, and showed me some code that really surprised me. So there was a declaration of a mutex semaphore, so semaphore mutex 1, and that's initializing the count to 1. And then later there was this assignment of the mutex back to 1. It had mutex equals 1. And I said, yikes, that can't be right. Because you can only call signal or wait on a semaphore after you've created. The student, of course, responded with the classic reply, well, the compiler accepted it, which of course must make it right. So what's happening here? Well, I got bitten by a combination of default assignment, meaning if you don't specify an assignment operation, then the compiler will define one for you. And I also got, together with that, the feature of using a constructor to do implicit type conversion. So the compiler sees mutex equals 1 and says, well, let's see, you're trying to do assignment. Now, you didn't define assignment on a semaphore, so I'll define one for you. But of course, it assumes the right-hand side is also a semaphore. So then it says, well, can I make that 1 into a semaphore using a semaphore constructor? And the answer is yes. So it generates a call to create a new semaphore, and it copies the semaphore's storage into mutex. Well, of course, this wasn't what I wanted to have happen. Now, if I had used a kit, I would have avoided this problem completely, because the constructors are not visible through the interface, so the compiler can't use them to do implicit conversions. The code to create a semaphore would look something like semaphore star mutex equals thread kit, or whatever the name of your kit is, arrow semaphore of 1. That's one benefit, extra benefit of kits. Another extra benefit of kits shows up when you try to distribute objects across a network of machines. Constructors have two problems in the distributed case. First, how do I construct an object on a remote machine? C++ constructors are only defined within a single address space. So it doesn't make much sense to say, create me an object over there. The second problem is you need to provide complete context when creating an object in a distributed system. This is because you don't have global variables in a distributed system. At least you prefer not to, because in a distributed system, we all know the word global means bottleneck. So using kits to create objects indirectly has many benefits. And this is a really important technique to encapsulate a group of classes. Inheritance is what distinguishes object-oriented programming languages from other programming languages. Inheritance is therefore a very important part of C++, but inheritance is also difficult to master. I don't consider myself a master, but I've learned some things the hard way during the development of interviews in Fresco. Inheritance is both good and bad. It's good because it allows you to factor and reuse code more effectively, so you write less code. And hopefully that means you can implement things faster and with better quality than you could if you hadn't used inheritance. Again, that's the point of all this stuff. It's supposed to make it so you could build better code, faster, cheaper, higher quality, all those things. If we're not achieving that, then why do we bother using this stuff at all? One way to think of inheritance is that you can take a heterogeneous data structure and manipulate it with a homogeneous set of operations. So you could take like graphical objects, polygons, circles, splines, rectangles, all with different representations. Some are big, some are small, and they have a common set of operations. Say you can draw them, or you can ask for the bounding box of them. Okay, so you have a bunch of different things. They're represented differently, but you can do similar things to them. And that's really the power of inheritance. Now, inheritance, unfortunately, is also bad in some ways. It scatters functionality across several different classes. So you can't just look at one set of code and say, I know where this is going. You can't look at a call to draw now and say, oh, I know what code that calls next. Because the call to draw now might be calling draw on polygons, or might be calling draw on splines. You have to actually know the type information, and to know the type information, you have to understand all the data. Inheritance also creates dependencies that may cause surprises when you try to change something. We certainly had the experience of making a change to a base class in interviews that broke a subclass. I think everybody who uses C++ has this experience many times. And the problem tends to have the effect of making you less willing to make changes in either base classes or the inheritance hierarchy itself. Now, you might think, well, reducing the amount of change to base classes is good, and it is good in some ways. The problem here is that we haven't separated the implementation changes, which we want to make easy, from the interface changes, which can be discouraged, or it's okay if they're harder, because presumably they don't happen as often. One alternative to inheritance is composition, and composition is often better. I mentioned the button example before. When we made interviews objects cheap enough, we could compose a button out of at least two objects, one for input, one for output. This change made for a simpler, more flexible implementation. So even though one way to build something is with inheritance, you should think about whether composing objects might work better. And we certainly found that composition for buttons has been a big help in terms of structuring our system. I'd like to distinguish inheritance of interface, which I'll call subtyping, from inheritance of implementation, which I'll call subclassing. Now, these are just my terms. C++ doesn't make this distinction. C++ just has a single kind of derivation that inherits both interface and implementation. But when you use C++ and you derive a class from a base class, you really should think about whether you're doing so to share the implementation of that base class, or whether you're just trying to share the interface. If you're not trying to inherit the implementation, then it's probably not a good idea to do so accidentally. So you can avoid that by making the base class abstract. Use pure virtual functions and no data. If you're not really trying to inherit the interface, which means you're saying this subclass really has to provide the same interface as the base class, then instead of using derivation, what you can do is you can define a member function that returns the kind of object you were considering inheriting from. So let's look at an example. You were thinking of class B, say, being a subclass of class A. So B derives from A. And instead of doing that, you can say, well, let's just define B as having a public member function that returns a pointer to an A. Now, this sort of issue of should I use subclassing or not, or how should I use inheritance, occurs several places in interviews. Glyphs, which I mentioned before, are these cheap, lightweight graphical objects. They can be aggregates. They can have a list of children glyphs, so that you can group several graphical objects together and treat them as one. You can transform them. You can do various operations to them as a group. Now, we could have derived glyph from a list class that provided the various operations for adding and removing children. So we could have made glyph a subclass of list, some sort of list class. But that would have created this dependency that didn't seem necessary between the glyph class interface and the list class interface. We didn't really want to promise that glyphs would be lists forever. And we didn't really need to use glyphs in places where we would use lists. We weren't going to pass a glyph to somebody who was expecting a list. So this relationship was not really the classic is-a relationship. Instead, we treat the list of children as something the glyph has and provide some member functions so you can access the list. So it's a has-a relationship, not an is-a relationship. Now, the glue example that we saw before, when the layout, we were talking about layout, it's really an example, a classic example of implementation inheritance. The glue class is really saying, well, I'm derived from glyph. I'm not adding any new member functions other than a constructor. And when you've encapsulated your class library, the way I talked about, then implementation inheritance isn't visible. We already decided that. So that's nice. Now we can make changes to the base class implementation without worrying as much about breaking code. We might break our code, but we're not going to break people who are using the library code. So that's a big improvement. Now, every inheritance discussion leads to a discussion of multiple inheritance. It tends to be a rather controversial topic. And C++ supports multiple inheritance, and it kind of supports it in two different ways. One is this notion of using virtual base classes. And when you use a virtual base class, if you have a diamond in your class hierarchy so that you have one class that appears twice, if you use virtual base classes, you only get one copy of that class's data. Semantically, you get one copy of the object. If you don't use virtual base classes, then you get two, or more generally, you get one copy for every time that class appears. Now, conceptually, virtual base classes are almost always the right semantics. I have yet to see a realistic example where virtual derivation, where non-virtual derivation is appropriate. Unfortunately, the bad news is that virtual base classes are pretty expensive with today's compilers. So you have the situation where it's kind of the right thing semantically, but it's kind of the wrong thing in terms of implementations. So here's a simple example. We have this common class, which is at the root, called base. And we have an interface class A and an interface class B. And we have an implementation class A-impl, which implements A, and B-impl, which implements B. It's really natural to want to use the implementation of A, that is the A-impl class, as part of B-impl. But this, of course, creates a multiple inheritance diamond. So if you think about it, you say, aha, well, I should use virtual base class derivation here to make sure that there's only one copy of A in that B-impl. Now, you look at this picture, and the numbers tell you the bad news with respect to virtual base classes. The first set of numbers are the sizes in bytes of instances for each class when the derivation is virtual. Yikes, 68 bytes for B-impl. And that's just overhead. It doesn't do anything. There's no data in B-impl that's of any value. So that looks pretty extreme to me, especially if I'm interested in building lightweight, cheap kinds of objects. Well, what can we do about that? Well, you could try to fix your compiler or maybe change the language or something, but that's not a very practical choice. So what you can do is use the idea of delegation and see if that works better. The idea of delegation is one object forwards, or delegates, some of its operations to another object. In this case, what we can do is instead of deriving B-impl from B and A-impl, that is, multiply inheriting it, we can derive B-impl just from B. And then what we'll do is we'll put an A-impl data member inside of B-impl. Now, any operations defined on A, whose implementation we want to reuse from A-impl, what we have to do is we redefine those operations on B-impl, and then the implementation of those operations simply forwards the call to the A-impl subobject that's inside the B-impl. So let's look at an example using the classes I had before. Suppose A defines an operation draw. B-impl has to define an operation draw too, and this operation would simply call the draw operation on the A member variable, which is the A-impl that's inside of B-impl. Of course, if there are additional parameters, then you have to pass those along, and if there's a return value, you have to return that back from the call. But the general idea of delegation is you're forwarding this call to this object that's inside you instead of inheriting the implementation. Now, the reason this all works is because the inheritance we're doing was for the purposes of implementation. This is important. It's not visible to the user of this library. So A-impl and B-impl are implementation classes, and we already decided that we're going to hide implementation classes. So what's happened when I did delegation is I can no longer pass a B-impl object to somebody who expects an A-impl parameter. Okay, and that's gone, that capability is gone, but that's okay because that's all implementation stuff, and I'm the only one affected. That is, whoever's implementing the classes A-impl and B-impl is affected, but the user of the library, who's presumably using A's and B's, is not affected. Now, I have to say that I was pretty surprised to find that this simple form of delegation I've described, I should say in object-oriented literature, there are more sophisticated issues with respect to the precise definition of delegation and how it all really works. So this is a pretty simplified model I presented. But I was really surprised that this simple strategy actually results in smaller amount of generated code and data. Maybe someday compilers will make all this work, virtual derivation. Maybe they'll make it efficient. But for now, this is a language feature that you really want to think carefully about before using. There's an idea related to inheritance where you want to attach some operation to another object. In user interfaces, this is referred to as a callback because the user interface code, like a button, calls back into the application at a specified function in the application when some input event occurs. Now, I refer to this idea more generally, and other people also use this term, wiring, because what you're doing is you're connecting up the control flow that goes from one object to another when some event occurs. I say this is similar to inheritance because at first it might seem like inheritance is the right way to code the solution to this problem. In the button example, you could think of a virtual function on buttons called press that's called when the input event is received. The base class doesn't define the implementation of press, and the application developer then derives a button subclass that defines the press function. Now, there are a couple of problems with using inheritance here. First, the action you want to execute when the button is pressed usually has to access other objects. And typically what you find yourself doing is you write this subclass, and all it does is it calls some operation on some other object. And that does the real work. So you say, well, why did I have to go to this work of doing a subclass? That's one problem. The second problem with this approach of using inheritance is that it isn't very easy to have several references to the same action. So in user interfaces, again, this happens when you have, say, a menu item, which is sort of like a button, and you want a keystroke to be mapped to the same action as a menu item. You wouldn't want to define that operation in the menu item subclass. Okay, that operation needs to be shared between the menu item and the keystroke interpretation. So you really want it to be a separate object. So inheritance doesn't quite work there. Now, as I mentioned in earlier versions of interviews, of course, we did it the wrong way, and we used the inheritance approach. And then later, and now in Fresco, we have defined a class action, which represents executable objects. The class simply defines an operation called execute. Now, for things like buttons and menu items, there aren't any parameters that you pass from the button or values returned to it when you're performing this operation. So this is a general mechanism. It'll work for other kinds of callbacks or other kinds of wiring. And in that case, you may pass some parameters. But in our case, we're not passing any parameters. We're not getting any result back. The other thing about user interfaces is that typically you want to support undo and redo. So in this case, our action class also has an operation to test whether the action is in fact reversible or whether you can undo it. You need to do that because if it's not reversible, then you should not put it on an undo list. Okay? And then there's the operation to actually try to undo the action. Now we have to figure out how to create these action things. So we got this notion of an object which encapsulates the control flow, that sort of jump to the actual operation. And the question is, how do I create these things? So to create them, typically you want to create an action that simply implements execute by calling a particular member function on a particular object. An action might also be implemented by interpreting a script. Okay, that's another thing you could do. But the key thing is the button, or in general the thing you pass the action to, it doesn't know how execute is implemented. It just says, oh, I have this action. When I want it to be executed, I just say execute on it. Okay, so we can use this template here to define a function that creates an action given an object and a pointer to a member function on the object's type. And this sounds sort of complicated, but in fact, it's a simple idea. You have to use a template because the type of the object and the class that the member function works on, they have to be the same. Otherwise, you can't guarantee that you can really call that member function and have it work. On the other hand, we want to be able to create one of these actions for really any type. So we want to be able to take any type and a member function defined on that type and say, okay, we have an object of that type and we have this operation on that object. Let's put those together and call them an action. Okay? Now, to implement this template function, there are a couple of possibilities, and I won't go into them all. I'll just mention a simple way, which would be to define a template class that is a subclass of action. So it's actually derived from action, and it implements this execute function by simply calling the member function that you defined with it on that object. So callbacks or wiring is really, if you think about it, it's a composition mechanism. It creates a control aggregate instead of the data aggregate that we're used to building with objects. And as such, we saw before, doing composition is not where you use inheritance. So when you're doing things that feel like wiring, you're really connecting up two pieces of your system, and you're connecting the control flow from one to the other, inheritance is not appropriate, at least not as part of the programming interface. Remember that perhaps we could use it as an implementation to create these little objects that really do the connection between the other objects. But the inheritance is not part of the interface. C++ offers a lot of power. Classes and inheritance are wonderful language mechanisms for reducing the amount of code you have to write and making code easier to change. But with the power comes danger, and some features, like implicit conversions and default assignment, are more frequently used inappropriately than not. Inheritance is somewhere in the middle. I mean, inheritance is really wonderful and it's great to use, but it's also easy to abuse, especially multiple inheritance. What makes C++ appealing, I think, is the relative efficiency and broad availability when compared to other languages. The efficiency people refer to, of course, is the compiled code. There still are some major inefficiencies in what a programmer must do when you use C++. Memory management is a big pain. It really is a big pain, and it's also frustrating how slowly good compilers and the other tools that you would like to have there in developing C++ code, how long it's taking for them to become available. Of course, what any language offers is just the mechanics. We, the programmers, have to provide the brains. I've talked about two general areas I've learned through experience how to use C++ features. The key lesson of encapsulation is that the interface to the whole, a group of classes, is more than simply the collection of interfaces to the individual classes. In particular, there are lots and lots of very good reasons to create objects indirectly using something like kits. The inheritance lesson is really to think about instances, the objects, instead of classes. We used to spend time in interviews thinking about class hierarchies and how to organize things. And now that's the last thing we think about, literally the last thing, because the first thing we think about is the alternatives. Should we use composition? Should we use delegation? Is wiring the right thing here? And to do that, you have to think about, in the overall design, what are the objects that you're actually going to create? And you have to keep in mind, when you're using inheritance, the conceptual differences between inheriting an interface and inheriting an implementation. These differences will be reflected in the way you define your classes in C++. What's going to happen in the future? Beats me. No, just kidding. I think we're still progressing up the curve on separation of interface and implementation. If you want to allow an implementation, for example, to reside on another machine, or maybe be implemented in a different language, you have to go a step further in terms of making that separation really strong between interface and implementation. This is part of the set of ideas behind Corba, the Common Object Request Broker Architecture, which is a standard developed by the Object Management Group. Corba has an interface definition language called IDL that's similar to C++ header files, but expressly eliminates any implementation or address space details. Microsoft's Olay also has a similar mechanism for defining abstract interfaces. So the trend here is you use these interface definition languages to specify the interface to your system or your class library or whatever pieces of your application you want to separate. A translator or a compiler, whatever you want to call it, can then automatically take this interface definition language that you've written and generate C++ header files, as well as RPC stubs or other information. And they can take an interface described in IDL and generate this automatically. Now, the work we've been doing with Fresco, we actually use IDL to define all of our interfaces. And we've written a little translator to C++ to get some experience using IDL and using it in the context of doing C++ development. We therefore use C++ as the implementation language, and we use IDL as a way to define the interfaces. And I have to say, based on our experience, that I really like this stuff. Because what I'm able to do is, instead of using a set of conventions with C++, I can work directly at a higher level. I can write the interfaces in IDL, and then I'm absolutely sure that those interfaces are completely abstract, and there's the opportunity to make them work in a distributed environment. Perhaps best of all, I can actually write less code now because more is generated for me automatically by these translators. Now, another part of this move to really making this separation of interfaces stronger is the ability to generate runtime information that supports dynamic invocation. Now, this may not sound like interfaces, separation of interfaces and implementation to you, but what this really means is, from, say, a scripting language or some interpreter, we can call operations that we've defined in the interface. Dynamic invocation, which is a standard part of systems like Corba and Olay, means you can create a request object, fill in the operation name and parameters, and then call invoke on it. Now, an interpreter for a scripting language or some other language is responsible for control flow and variable substitution and all the sort of language stuff that it has to do. But when it's time to perform an operation that you've defined in the application somewhere or that's part of the system, what you'd like is to be able to just have that interpreter say, okay, I'm going to go off and use dynamic invocation to do that. Now, what does this all mean to the programmer? Well, this means all you got to do is define the interface, and with no extra work, the implementation that you build for that interface will automatically be accessible in a much more dynamic environment. So let's return and think about what this would mean to the interviews document editor that we saw before. What would these trends mean? Well, they're kind of two things. The types of objects that make up the parts of the document, we now define these in terms of IDL. So the tables and the figures and the text, we would now define these in IDL. And that means that we could have implementations of these parts of a document running on other machines, and they could be doing simulations, and we could have more dynamic elements of our document, and they would all appear in the same window. And the application developer didn't need to worry about this at all. That's the beauty of it. The fact that it can be distributed comes for free. Well, it doesn't exactly come for free. A more accurate statement would be that we've already paid for it, because there really is a fair amount of effort in defining interfaces in IDL. We went through the experience going from interviews to Fresco of really taking things and saying, okay, we're going to use strict interfaces. We're going to have a strong separation. And that's a fair amount of effort. So really, if you do that, you've already paid for it. Then distribution is free. The other thing is, if the user can locate objects in the network transparently or without worrying about exactly where they are, so you can find them, then the user didn't need to worry about distributed access either. So now you can imagine an environment where the applications and the users become less concerned about where things are located in a network environment. The other part of what this would mean to real applications is that operations, because you now have this ability to perform operations on an object with dynamic invocation, a lot of the control flow of the document editor could be driven by scripts, little scripts, let's say, and a user could come in and extend them or customize them. Additionally, you could have an editor be driven by scripts that are part of a larger collaborative environment. So really, the sky's the limit when thinking about all these possibilities. And there's just a lot of things that you can imagine doing with this sort of environment. But the implementation of this future that you imagine, it's going to require a lot of work and a lot of careful attention to the details, including how best to use things like encapsulation and inheritance in C++. Thank you for listening.